Right, guys, I'm going to pick up with this presentation then. So yeah, let's have a look at some answers, and you can see how you're getting on with your understanding here. So yeah, so now unfortunately I haven't got a cursor, so I can't annotate and draw on this presentation whilst I'm speaking to you. Okay, so you can see there were two representations in Boolean logic that you could have used for your answer if you've had a go at doing that in terms of what Q is equal to. I think the one that I would hope most of you have gone for is something on the right hand side. So the Q equals, and then we've got the not A, so the not gate right at the top. Okay, in brackets to show that there is an order of precedence here. So we've got the B and the C, so we need to AND the B and the C together first. Okay, so the brackets just indicates the precedence there, and then the fact that the result of B and C is then ORed with the value of not A, and obviously the OR being represented by the plus sign. Okay, so you know, if you've done it version number 1, that's also fine as well, and sort of written out the statements, but I'd prefer you to use the notation on the right hand side of that particular answer. So that is the equivalent Boolean expression for the logic gate, the diagram that you can see. Okay, so this idea about being able to convert between one and the other. Sometimes they might give you the Boolean expression and then ask you to construct the logic circuit diagram from that. Okay, so yeah, make sure you follow the order of precedence, and the brackets will help you do that in terms of constructing the circuit. Right, let's have a look at the truth table now. So the truth table, well, the first bit hopefully we can't go too far wrong with, because we just got to model the different, well, all the different combinations of inputs that we can have. Okay, so if we've got a circuit with 3 inputs, then that's 8 different combinations, isn't it, of bits that we could potentially supply into those gates. Okay, so if we take, for example, the first one, if we just work through one example so you can see how this works. I wish I could annotate, but I can't, so just try and visualize on the screen, and I'll try and make it clear where I would be annotating if I was able to. So we've got input A, so input A, and in this first column here we've got D equals not A, so I'm just going to list what happens, what D, the output D, is going to be as a result of values being passed through that NOT gate. So in this particular example, well, I'm passing the input A in, which is a 0, so not A is going to be 1, so D is going to become equal to 1. Okay, E, so my value for E, my output E, is actually the result of what's produced by the AND gate, and into the AND gate I'm supplying the values B and C. Well, in this, I'm still working my way across this top line, by the way. So in this particular example, both of those are 0. Well, 0 and 0 is going to equal 0, isn't it? So E is also going to be 0. I would be kind of just like annotating this onto my circuit diagram as well. Actually, I find it quite helpful to do that when I'm working through these types of questions. And then I just need to get to the final point where I'm going to OR those two values. So I'm going to OR D and E. Well, I know that D is equal to 1 and E is equal to 0, so the result for Q there is going to be a 1, isn't it? Because in an OR gate we only need one of the inputs to be true for Q to be true. So let's reveal that. Now you just need to work your way through that for each particular row, and if you've done that correctly, then this is hopefully what you've wound up with at the end. Okay, so you can see on that first row we said that Q was a 1. Okay, and that's how we got there. Okay, so I'll leave that up for a second, and you can just have a quick cross-reference and see how you've got on. Okay, and then I am going to move on now. So you know this is being recorded, so you can come back and you can sort of check every line there carefully to make sure you're happy with that. Okay, and that table is obviously the equivalent of the circuit diagram, and also therefore the equivalent of the Boolean expression as well. Right, so let's have a look at some other gates that you also need to be aware of. So it's not just AND, OR and NOT. You also need to know about the NAND gate. Okay, so the NAND gate. So let's have a look at it first off in terms of its symbol and its notation. Okay, so you can see it looks very similar to an AND gate with the addition of the circle, which we also saw on the NOT triangle, didn't we? Okay, so quite handy to remember that really. So it is the same as the AND gate, except the addition of the circle basically means it's a NAND gate. So what does that actually mean? Well, let's have a look at a truth table for this. And you can see the definition. So the output is true if any input is false. So if you were to work, I'll give you a second to maybe visualize what that table might look like. So if any input is false, the output is true. Okay. Now, if you've worked that out correctly, you can see it's basically the inverse of an AND gate, isn't it? In terms of we're turning Q to 1 whenever, well, basically the only time we pass through a 0 is when we pass into two ones into the gate. Okay, notice the slightly more complex Boolean equation here as well. So we've got the A and the B, and then the overhanging bar to represent the, well, almost like the NOT, isn't it? The NAND part of this definition. Okay, so that's the Boolean equation. And just also, final thing to point out here is, and it's quite nice, is the NAND gate, but I'm not going to tell you why at this particular moment in time. It's known as the universal gate. But why is it known as the universal gate? When you start doing some of the exercises after this tutorial, you hopefully be able to establish that for yourself in terms of why would it be called the universal gate. So see if you can figure that one out later. Okay, well, you can possibly have a guess as to what this particular gate is going to be based on its shape, because we've got that arrow shape again, and then we also have the circle at the point of the arrow as well, and this is a NOR gate. Okay, so a NOR gate, and this, in this particular one, we can see the output is true if all the inputs are false. Okay, if all the inputs are false. So again, if you want to maybe run through that truth table and see if you can fill it in before I kind of announce it. And then let's remove it and see what we've got. Okay, so you can kind of see that a NOR gate is pretty much the reverse of an OR gate. Okay, and the only time we're going to pass through a value of 1 is when both the inputs are false. So if A is a 0 and B is a 0, Q will be a 1. Okay, and again, if you notice, the sort of beginning to see the logic now behind the Boolean equations. So we have the A plus B, so the plus representing the OR, and the overhanging bar representing obviously the NOT aspect, so the NAND aspect of this particular equation. Okay, great. And then if we tab on again, we're on to our final gate that you need to be aware of, and slightly unique design, this one. So again, be very careful with how you draw these in the exams, of course. So you'll notice that you've got two inputs, A and B, as usual. We have the arrow, which looks similar to the OR gate, but just notice here this gap between the A and the B, and they're not sort of directly connected into the arrow. Okay, and this is a XOR gate. Okay, so this is a XOR gate, and I think, I mean, we have touched on this once or twice in class this year. You could probably have a good go at doing the truth table for this particular gate, and if we kind of reveal that, you can see that this time we only pass a 1 when one of the values is true and one of the values is false, or one of the values is 0 and 1. But the presence of 0, 0 or 1, 1 would result in a 0 being passed an output from Q. Okay, right, so they are the gates that you need to be aware of, and the truth tables, and definitely make a note of these Boolean equations, because we're going to sort of build on that a lot next week, but also you're going to have a practice at converting between these circuit diagrams and Boolean expressions and vice versa. Okay, so that's all going to come up in the practice worksheet that you've got. That's the plenary for the end of today, so I won't worry too much about that for tomorrow. I think, so for now, we'll probably give you that as a starter tomorrow. But that is the end of the presentation, and that should give you enough information to get up and running with the exercises in the worksheet. So if you want to work through those worksheet exercises, if you can do them on paper, that's ideal. Just in terms of submission, if you could scan them in or take photos of them. If you're taking photos, you can get some decent apps that are particularly good at sort of just taking photos of written work, and they cut out all the well, they can cut out and just recognize the sheet of paper, so you don't end up with better quality photos that get uploaded. So if you could compile those photos, put them into a Word document and upload them, something like that, that would be perfect. If you cannot access a printer, then possibly annotating on top of the Word document might work if you can do so. Now, if you're lucky enough to have a stylus, then that should work and be fairly, work fairly well, and you can just submit the finished document. If you've got a mouse, your artwork is going to be slightly well, probably not as accurate and as neat as you might want it to be. Don't worry too much, just as long as I can see the actual circuits and the actual diagrams, and I can interpret the symbols that you've used, then we'll sort of take that as the best approach for now. Okay, so do what you can with that, but please do make sure you've submitted your work by the end of today, and then tomorrow I will release the answers for you to be able to check and check your progress against them and see how you've got on. Okay, any questions, please do fire away, and enjoy. Yeah, I quite like Logic Gate, so yeah, have fun. See you tomorrow.